Okay, so you had a question?
Yeah, so I was just working through like Noether's theorem, deriving the Noether current, and I realized...
Noether's theorem?
Noether's theorem, yeah. And deriving the Noether current, right, given some symmetry, maybe you have some Lie group. And I don't really understand why there's a part where you get a term. Can I just like write something on the board really quickly? Okay?
All right.
I'll just like write in the corner very small. Anyway, eventually you get a term that looks like delta d mu phi j. If you have some phi that's some vector field, you get something like this, right? And normally we would write something like, okay, if you do the symmetry transformation on phi j, right, this should give you like some, I don't know, some parameter times whatever your generator is and the jk element of it on phi k, right?
Right.
But what we do is we usually just pull this derivative out, right?
Yeah.
So why don't we have to transform the indices on the derivative? I don't really understand why we don't need to transform.
I think you do.
All right, let me tell you.
I think you do it. They just go away.
Oh, you do, but
it's
they
like
go
a
away.
functional. It ends up being like the form of a functional derivative, doesn't it? I think I don't know. I haven't looked at that in a long time, but I'm pretty sure you do. It just less.
Okay. All right. If I can say the way I think about these things is under the transformation, phi prime is phi plus delta phi j, and so the derivative d mu of phi prime is the derivative of phi. I guess you had a j on these, but all right, put a j if you want. Okay, so phi prime j is phi j plus the change in phi j. So the derivative of phi prime j is the derivative of phi j plus the derivative of the change in phi j. And so the change in d mu phi j is the derivative of the change in phi j.
Okay.
And I think that answers, I hope that answers your question.
Why wouldn't it be, but I feel like you sort of...
So it's d mu on all this, I guess, epsilon a t a j k.
Yeah, sure. But I feel like you've kind of written the answer already though, like with your d mu phi j prime, d mu phi j, and then your d mu delta phi. Shouldn't it be delta of d mu phi j?
Well, what is delta d mu phi j? It's d mu phi j prime minus d mu phi j.
I know, but so then I feel like
in other words,
sort of go in
this
circles
is
there. It's okay though.
This is d mu of phi j prime minus d
delta d
mu of phi j. That's the change in phi.
Oh, sure.
Change in the derivative is the difference of the two.
I see that you subtracted it across, but you set yourself up to get the right answer from the get-go because you already pulled the d mu outside of the
but that's the way it works in every case.
Okay, yeah. I don't know. Yeah, okay. Yeah. I'll have to try what you said.
This is something that bothered me a great deal when I was a graduate student, actually.
Yeah.
That's the way you were talking about doing it is written. It's in Eskin short.
Yeah, that's where I think
they got
that's
a
either there, and then they do it. It comes up a lot in like algebraic geometry books. You'll see like a really formal version of it.
Well, it comes up everywhere, even in undergraduate.
Classical mechanics is the first.
Classical mechanics, undergraduate classical mechanics, which I hope somebody teaches somewhere.
Well, I think it comes up, but this notation is. I don't think it comes up with this notation.
Yeah, people very rarely tell you what the answer is. What they do is they skip from this to this without telling anybody why it works. And I know when I was an undergraduate, I was quite puzzled. Graduate student, I was quite puzzled by that. And so in the in the book I wrote on mathematical physics, or physical mathematics, I explained that in two or three places. At least I hope I did it correctly. Let's see, I promised that I would not talk any more about neutrinos, but I realized I had left something out. So let me put in what I left out, which is the most it's actually extremely simple. The only thing I think that I was going to leave in, that I skipped, is well, let me just remind you that if you do the effective field theory approach, what you get is you get a new term in the low energy theory, which is basically g squared v squared over 2m, and then some nu bar nu. And this nu bar nu could be any neutrino flavor or mass, and we could be talking about Majorana neutrinos, or we could be talking about Dirac neutrinos. This thing would come from a high energy, from terms in a high energy theory that would look like this: minus psi bar d slash plus u gem psi plus g psi bar some sort of Higgs transpose sigma to L plus G L bar sigma to H star psi. So psi is a heavy fermion field. H is some heavy Higgs, unrelated to the other, but it transforms under SU2 left. And L is the usual doublet. And I'm just considering one family, the electron, so that's the electron neutrino. Anyway, you take this thing, you complete the square, and you shift, you functionally integrate over psi. And complete it. Well, first you drop the derivative term, and then you get L psi 0 being minus m, and you complete the square. And then you get minus m psi bar minus g over m L bar sigma to H star times psi minus g over m H transpose sigma to L plus g squared over m L bar sigma to H star H transpose sigma to L. Then, so this is, you just drop the high energy derivative terms, complete the square, and you integrate over the fermion field. That gives you an overall determinant that's field independent because you shift the fermion fields. And then what's left is this term, but in the vacuum, or in the low energy theory, H turns into simply what I wrote it as 0 V over root 2, I think is the way people would normally write it. And So this term gives you v squared over 2. And that gives you this term over here. And of course, sigma 2 squared is 1. And so that's the low energy term. And that low energy term, if nu is Dirac, then nu is 1 over root 2 L1 plus I L2 R1 plus I R2. So this is, Dirac's a 4-component spinor. L1 is 2-component left-handed, L2 is 2-component left-handed. They all have the same mass. And then that neutrino term, L nu bar nu, is minus m over 2. Well, m being g squared, or m squared, no, m being g squared v squared over 2m. So this coefficient here. This is then m over 2 L1 dagger minus I L2 dagger R1 plus I R2 plus R1 dagger minus I R2 dagger L1 plus I L2. So this is then a Dirac mass term. Or if nu is simply a Majorana field, where you just have one left-handed field and one right-handed field, then nu bar nu is equal to minus m L dagger R plus R dagger L. And it turns out for a Majorana field, we have the Majorana condition, which says that this is actually minus Im R transpose sigma 2 R minus L transpose sigma 2 L. So you can rewrite it that way. What I've got here is that L dagger, so let me decompose this, it's equal to I R transpose, I think that's R transpose sigma 2. And that's sort of a backwards way of writing, if you take the adjoint of that equation, you get L is equal to minus I sigma 2 R. And in the other case, this one was R dagger is equal to minus I L transpose sigma 2. Right. And if you take the adjoint of that equation, you get that R is equal to I sigma 2 L complex conjugate. And of course, over here I made a mistake. There's a star there. So this means that if you have a Majorana field, then it's of this form LR, but it's actually special. It's nu is equal to LR, but that's the same thing as L, and R is I sigma 2 L star. And star means you complex conjugate the numbers and adjoint the operators. I did not bring with me all the the details about that, but this Majorana condition is an automatic consequence of the way spinors are defined, if you define them correctly, the way Weinberg does. And the Majorana condition actually applies to the Dirac spinors as well. I unfortunately didn't think about printing up or wait a minute. Oh yeah, I did. Okay, hold on. Let me tell you a little more about this because it's something that I didn't mention much because, I guess because I didn't know. Well, anyway, I didn't mention it much. So let's go back to the Dirac case again, and just a general field. It doesn't have to be a neutrino. It could be an up quark or something. There, what we have is psi of x is this sum over spin states integral dqp over 2 pi to the 3/2, and then u of p and s e to the I of px, a of p and s plus v of p and s e to the minus I of px, a dagger of p and s. And I'm writing this for, well, I mean, literally, I've always thought that Weinberg was a little excessive in his N and NC notation, but I think it actually makes a lot of sense. So this is the annihilation operator, for example, for a red up quark. This is the creation operator for a red anti-quark. As opposed to the creation operator for a red quark. Those are two different particles, two different things. Now, it turns out that the spinors that we've defined carefully, and you will probably justly say too carefully, is that u of p and s is actually equal to gamma 2 times v star of p and s. So this, and moreover, v of p and s is gamma 2 u star of p and s. So these general relations follow from Lorentz invariants and so forth, and the way fields transform and so forth. This is Weinberg's construction of them. And let me remind you that gamma 2 in Weinberg's notation has a minus I here, 0 sigma 2 minus sigma 2 0. And his notation for the gammas differs from other people's largely because he wants to have, to use the right metric, which is the metric in which the space part occurs with the plus signs and the minus sign, and the time part has the minus signs, which is what makes sense. Now, these conditions here tell us that psi, which is equal to LR, if we split it up into its left and right-handed components, is equal to minus I, 0 sigma 2, minus sigma 2, 0, on L star R star. And this is then minus I sigma 2 R star I sigma 2 L star. Now, I actually skipped something. All of this is true in general, but for here, I'm talking about a Majorana field. Because in other words, the Majorana conditions are psi star equals gamma 2 psi, and psi is equal to gamma 2 psi star. And so these are true just for spinors when they're correctly defined, and this is true, this is a correct expansion for Dirac or Majorana fields. But Majorana fields are special in that psi star is gamma 2 psi and psi is gamma 2 psi star, and that implies that psi is equal to, this is psi is equal to gamma 2 psi star, and when you do the psi star, you get that, and that tells us that for a Majorana field, L is minus I sigma 2 R star, and R is equal to I sigma 2 L star. So you see, for a Majorana field, you have an N here, and the conjugate particle is the same particle, so this N conjugate is just N. So if you take, let us just construct this thing, minus I sigma 2, or gamma 2 here, minus R. If we write, that's just simply gamma 2. And now let's take this thing, we want to take psi star, so psi star will be L star R star. Okay, so this is gamma 2 psi star is equal to that. But now, what is L star? Well, in L star, in fact, we have, it's really gamma 2 L star R star. And if we have a gamma 2, when we take the star, this turns into an A. We've starred this. Gamma 2 V star is U, so now we have UA. And maybe I should do this again. Let's write gamma 2 psi star for the Majorana case. This will be integral dqp 2 pi to the 3/2. So then it'll be gamma 2 u star e to the minus I px a dagger plus gamma 2 v star e to the I px a. Okay? So that's gamma 2 psi star. But now, all the spinors satisfy these relations. Gamma 2 u star is v and gamma 2 v star is u. So this is v and this is u. And so now we see that this is just the same field psi. Okay. And so for a Majorana field we have gamma 2 psi star is psi, and consequently psi star is gamma 2 psi. And now if we write that in terms of left and right fields, then we get this equation, which then tells us that the two-component right field starred with multiplied by minus I sigma 2 gives you the left-handed field, and similarly I sigma 2 on the adjoint of the, or the complex conjugate of the left-handed fields gives you the right-handed field. And that's for Majorana, that's just for the Majorana case. All right, so that was, I just thought it was good to explain these things. This is another reason, by the way, why Schwarz's spin is wrong. They don't satisfy these Majorana conditions. All right, neutrino oscillations. These are the things that were discovered over the past, I don't know, 40 years or so. Originally, in some courageous experiments by, God, his name was in my head and then I just now forgot him. Does anybody remember?
What did he do?
Ray Davis, I think, was the person who did these first chlorine experiments in a deep mine. He used tons of cleaning fluid. And what he saw was that there were only a third as many neutrinos from the sun as Cahill and others had predicted from their models of the sun. And so let's suppose we have a neutrino of energy E that goes a distance L in a time t, and then the phase that it gets is e to the I PL minus ET over h bar if I use universal units. Now neutrinos are nearly massless, that is to say their mass is of the order of less than an eV, and consequently Cm over P is essentially 0 and T is essentially L over C, so they're moving essentially at the speed of light. And so the argument here, PL minus ET, is PL minus square root of C squared P squared plus C to the fourth M squared L over C, L over C being T, and this is then PL minus PL times the square root of 1 plus C to the C squared M squared over P squared, and this is approximately minus C squared M squared L over 2P, and on the other hand, E is essentially CP to many significant figures, and so the change in the phase, if you have you see what's created when a neutrino is created, an electron neutrino is created somewhere, you have here a E1, a state of nu 1, plus UE2, a state nu 2, plus UE3, at least this is the current thinking, nu 3, where these are mass eigenstates. We need new language. This word eigenstate, eigenvalue, there's too many syllables and it's kind of a stupid word. It's brought over from the German, German by people who didn't really speak English, and whose native languages were not English, and so we're stuck with all these ugly terms which we should really replace. Anyway, this is the electron neutrino that is created initially, And then each of these mass eigenstates propagates with a different mass. And in particular, if we just go do the 2 neutrino approximation, then delta phi is minus c cubed m1 squared minus m2 squared L over h bar e. And this is written as minus c cubed delta m squared 1, 2 L over h bar e. So there's a phase then that shows up and is proportional to the distance you travel divided by the energy. And in the case of the Ray-Davis experiment, the neutrinos were coming from the sun, and so L was huge. There were other effects, though, involving what happened to the neutrinos as they went through the sun. And I guess I should mention that on the fly. So you have an electron neutrino as it's, let us say, going through the sun, it can scatter off an electron. So what you have is the electron neutrino releases a W. There's an electron here that absorbs the W, that absorbs the W plus and becomes an electron neutrino, and the electron neutrino comes out. So there's this forward scattering of nu to nu due to the exchange of a W, which is separate, of course, from that effect. But the electron neutrino can do another thing. It can go across like this and just exchange a Z0 with an electron or a quark or whatever. The Z0 can interact with anything. And, well, not with anything, but with a variety of quarks and leptons. And so the electron neutrino does that. Notice, however, that a nu mu can't do this. A nu mu can only do Z0 exchange. And so this is electrons or quarks. So there, another difference between electron and muon neutrino shows up because of their different flavors as they go through the sun. Anyway, I just thought I'd go over these things that we weren't talking about last time, or that I hadn't yet done last time. So let me now begin to fulfill a promise I made mainly to Austin, but I suppose to everybody else as well, of saying something about the quantization of fields in curved spacetimes. And it turns out that this was, as far as I know, first done by a Russian physicist many years ago by the name of Bogoliubov or Bogoliubov. And I don't know if there's an I in there. When I was a student, I heard people say, or I thought I heard people say Bogoliubov, and I then said that. There's a book by Burrell and Davies which I don't really recommend, but I don't know of a better book yet. So if any of you know of a better book on quantizing fields in curved spacetimes, let me know. Okay? In any event, let's just talk about scalar fields for simplicity. So we have dqp over square root of 2 pi cubed, 2p0. And I'm going to write a 0 on this because I'm going to talk about, this is the field expanded in terms of flat space annihilation and creation operators, and in terms of mode functions here, which I'm going to call f0p of x, which is just e to the I px. These, of course, are solutions of the Klein-Gordon equation, box minus m squared which means that in other words, we use these mode functions because they're solution of the Klein-Gordon equation, and once we use them, then automatically the field, because it's expanded in terms of mode functions that satisfy the Klein-Gordon equation, the field satisfies the Klein-Gordon equation. Which, of course, is the same thing as box minus m squared. Now, if so I'm going to rewrite this expansion in a in more explicit terms, it's going to be A0P F0P of x plus a dagger 0 of p F0P star of x. Now, this was all flat space. Now, in curved space, we don't have the Klein-Gordon equation. We have something else. So this changes to, and what it changes to is square root of g, gij, dj, phi of x equals m squared, or if we want to make it look as much as possible like the other expression. In fact, we want to make it look as much as possible. We'll divide by square root of g, and then just subtract m squared phi of x equals 0. So this is the Klein-Gordon equation in curved space. And here, by curved space, what we mean is that the invariant distance is gik of x dxi dxk. G is the absolute value of the determinant of the metric. Different people use different notations. Some people call G the determinant of the metric, and then they have minus G in all their equations. I think that it's better to get rid of the minus sign once and for all, and since we're going to define G anyway as something new, we might as well define it as the absolute value of the determinant. So, what we do then, and remember that over here, we wanted to have the Klein-Gordon equation, the field to satisfy the Klein-Gordon equation, so we expanded the field in terms of mode functions that satisfied the Klein-Gordon equation. Here, we've got a GR version of the Klein-Gordon equation, so we want to expand the field in terms of functions. So let me do that. phi of x as an integral d cubed p over square root 2 pi cubed 2p0. And now I'm going to say a of p, f sub p of x, plus a dagger of p, f star p of x. So this is the field with curved space operators, AC operators. So AC here is annihilation creation.
Can I ask a quick question?
Okay, good question.
Yeah, so I remember that the reason why we have like 2p0 in the bottom
Yeah.
had something with trying to define some Lorentz invariant
Right.
measure over which we can integrate.
Right.
And the p0 sort of, I mean, we sort of got at it from the dispersion relation of the original Klein-Gordon equation, right? So does the square root of 2p0 change at all? Or I guess just the form of 2p0 changes because
That's
dispersion relation is
actually,
change.
you know, you may be right. I just assumed that when I was writing this up, I assumed that we could go the same way. The actual way that this is normally done, so let me tell you what people normally do. Normally they write this more abstractly. They say phi of x is simply a sum over I, or let's not use I since we have an I, a sum over, say, k. Well, k isn't so great either. Let's use a sum over n. A0 sub n, fn plus f0n plus a dagger 0 n, f dagger 0 n, f stars. So that's what people normally do. I thought it would be clearer to use this notation, but you're quite right. When we go to curved space, one might need to modify this. I was assuming that the quantum numbers of the particles in curved space-time were essentially the same as the quantum numbers in flat space, so that we could use a 3 momentum and a 4 momentum and relate the 4 momentum to the 3 momentum. So let me give you two statements about this. One is that what people normally do is write it this way: a sub n, f sub n of x plus a dagger sub n, f n dagger of x. And because they just have a sum, they don't say anything about what the measure is, because they're just summing over things. On the other hand, I think I can justify this picture by saying that, well, what we're imagining is that we're looking at this field in a region that, so to speak, is flat space after these particles have come out, let us say. And it's also true that you can have examples in which you've got both. In other words, if you're just talking about, if you view the thing as an accelerating, if you view the curved space simply is an accelerating reference frame. You can imagine an accelerating reference frame in a Minkowski flat space. And then I think this is appropriate. But in what Davies does is he uses the sum notation. I thought it would be clearer to use to write the particles that way. In any event, the flat space mode functions obey this inner product relation. I d cubed x f star 0p time derivative f0q of x minus the time derivative on f0p star f0q of x and this turns out to be I integral d cubed x e to minus I px minus I q0 e to the I qx minus I p0 e to minus I px e to the I qx. And so you can see what that'll do. You're going to have two terms contributing, and you're going to have a delta function of momentum and a 2 pi cubed, and the i's come out appropriately. So this is 2p0, 2 pi cubed, delta cubed of q minus p or p minus q. And notice that this is then f0q, f0p complex conjugate. So that's a nice property of that inner product. Another property is that the inner product of fp with fq is 0, and the inner product I got that. Wait a minute. That's what I just computed. It's rather that f0p star, f0q star is minus 2p0, 2 pi cubed, delta of p minus q. So it's just minus that result. And then this one, and then two more things is that the inner product of f0p with f0q star is actually 0. Okay. So we can generalize that to curved space by saying that what we have is an integral, a square root of g sub s oh, sorry, we've got an integral already. D cubed s, and then we have a time-like future pointing vector n, and then we have fp star of x dA fq of x minus dA fp star of x fq of x. So that's the inner product that imitates this inner product. And what people do is they assume that the solutions, right, I should have written down what, well, I did write down in the notes, but I don't think I wrote down on the blackboard. What we're assuming is that square root of g di square root g, gij, dj, fp of x minus m squared fp of x. That there's a complete set of solutions to this equation, which we're calling fp of x. And then we're defining an inner product on this complete set of solutions in this way. And
So 1 over root g at the beginning? Before you had it. Oh, no, because the parentheses are around everything, I guess.
I'm sorry.
Sorry, I'm just saying, I guess the parentheses should be closed around everything, because before over here, we just have a 1 over square root g. But then I guess you didn't finish. So, but then shouldn't it be 1 over square root g if you're doing that?
The very first, the coefficient should be inverted 1 over root g in the front. Is that, or is it just root g?
Right.
Also, does this equation have a name?
I don't know. I imagine people just call it the first space time golden equation.
Okay.
I don't know quite what this. You get 2 candies for pointing out a mistake.
So he
Anybody else hungry?
Let's split the well.
Anybody hungry?
I have a question though.
All right, yes.
Next last equation after the d cubed s, is that an n or an m or?
Over here.
Yeah, right after that. What's the next, what is that?
Okay. This is a future pointing time-like vector.
Okay.
And d cubed s is a space-like hypersurface, or let's just call it a surface. So this is the analog of d cubed x. And
Sorry, what
let me just, yeah.
Sorry, I was just going to say, what is future pointing? Does that have something to do with the inner
N.
product of it with itself? No, what does it mean to be future pointing?
Well, it means that it has a positive time component.
Okay.
And over here, G lower ij, of course, is the metric of space-time. G upper ij is the inverse metric. So that is delta ik. So that's what the G upper ij means here. And this is basically the covariant Laplacian. In the chapter on GR in my book, I explain why it is that the covariant Laplacian turns out to look like this. And in fact, this is actually much simpler than what you'd expect. In other words, if you just started out with writing down covariant derivatives, you see, when you have dj of phi, this is a covariant vector. But then you want to take a covariant derivative of that covariant vector. And if you wrote that down from first principles, you'd get something that was quite messy. And it turns out that because of the properties of determinants, that turns out to be just this, which is a lot simpler than it could be otherwise. So in other words, all you have is the inverse metric. You have this thing that's just a function. and again the function and a derivative. So it's much simpler than it would be otherwise. Otherwise, just one covariant derivative means you have these Christoffel symbols, which don't even transform covariantly because they're like gauge fields. So under coordinate transformation, they get an extra piece, just as gauge fields, when you do a gauge transformation, you get a nice transformation of them and then an extra piece. Okay, let's see where I was here. Okay, now if we go back to flat space for a minute, and we use the definition of this inner product, and we're going to use that same inner product for the curved space solutions. And in particular, if we use the discrete notation, then we're going to assume that the curved space solutions are just basically delta NM, and that this is the same thing as FM, Fn complex conjugate. Well, it has to be because it's real, doesn't it? Anyway, and that Fn star is minus delta Nm, and that Fm star is 0. Okay, and we're going to be assuming that there are, as I said before, that these form a complete set of functions, so we can expand any function that we're interested in terms of these functions. So now, in flat space, what we do is we say that A0 of k is the mode function, which happens just to be F0k with phi. So this is an integral dqp over, again, 2 pi cubed 2p0 A0 of p. And now we're taking this inner product F0k right, F0k with F0p, F0p being the thing that multiplies this, and then we have A0 dagger of p, the inner product of F0k with F star 0p. So that's the inner product of the flat space mode function with the field. And you see, if you just use these normal flat space mode functions, just the phase factor e to the I, this would be e to the I k dot x. This term will be 0, and this will give us a delta function. And so this gives us square root of 2 pi cubed 2k0 a of k. Well, A0. Yeah, A0. And so I should have written this as that A0 of k is this over square root 2 pi cubed 2k0, and so divide by 1 over that square root, and so then we cancel that square root at the end. And similarly, we can write A0K dagger is minus F0K star, the inner product of that with the field. And again, divided by this square root. I'll just write it as so this expresses the flat space annihilation creation operators in terms of the field and their mode functions. But if we can also expand the field in terms of its mode functions, and we can either use, assuming the quantum numbers are the momentum ones, or we can just say it's a sum over n, a sub n, fn of x, plus an dagger, fn complex conjugate of x. So that's another way. In fact, the purpose of this discussion, the advantages of using this notation are obvious. It's a much simpler notation. On the other hand, when you go from a continuous representation to a discrete representation, effectively you're putting the whole universe in a box, and that seems somewhat contrary to the spirit of cosmology. But anyway, let's maybe go with the simpler notation. In any case, what you then get is that the curved space annihilation operators is then the inner product of the curved space mode function, let us say Fn, with the field phi. And similarly, a dagger sub n is minus Fn star with phi. So in other words, in terms of this inner product, replacing the second mode function by just the field, one can extract the curved space annihilation creation operators from the field using the curved space solutions to the curved space Klein-Gordon equation. And so all of this is mathematically, it's fairly straightforward well, compared to 5-loop calculation of the magnetic moment of the electron. It's pretty straightforward and simple and easy to understand. But here's the interesting thing. We're defining the ordinary vacuum, as we usually do, by saying that it's annihilated by all the flat space annihilation operators. So I'm going to use this notation. And similarly, we'll define the curved space vacuum by saying it's annihilated by all the curved space annihilation operators. And the idea is that we're thinking of the field as being the same field, and then we can expand the field in terms of flat space creation and annihilation operators and flat space mode functions, or we can expand it, and we can expand it in terms of curved space annihilation creation operators and curved space mode functions. And consequently, we can write, and moreover, we're imagining, in fact, we're assuming that the mode functions of flat space and curved space are both complete. So that means that we can expand them in this way. That the curved space mode functions can be expanded in terms of the flat space mode functions with coefficients that we'll call alpha, and beta, and gamma, 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 and NM. And in fact, you might say we could get away with that, but in fact, we also have to have beta NM F I was writing 0M, so let's write 0M. F0M complex conjugate. So in other words, we're expanding the curved space mode functions, which are the solutions of the curved space Klein-Gordon equation, in terms of the free space Klein solutions and coefficients. And in general, these will be really integrals. But to avoid Austin's observation, Davies and Burrell use this discrete notation. And of course, we can go the other way. We can say that F0n of x is a sum on M. And now it turns out that consistency requires that this be NM F0m of x minus beta NM Fm star. So those are the other relations. So this allows us to express one in terms of the other. Now, this is what's, once we've got all of this apart from, again, a possible minus sign or a root 2 somewhere and so forth.
On your last equation there, inside the sum, that should not be F0M, should it? It should be just Fm of x?
Yes. Bobby's going to open a candy.
No, I don't need candy store. I already got Girl Scout cookies in the car.
You don't want any more?
Give me Austin.
Austin, you want one?
Austin needs one.
Anybody else want one?
He hasn't had one in a while.
So you look as though you've recovered.
Yeah.
You're feeling better? That's good.
Yeah, I go to SHAC, so
Did you, I'm sorry, did you go to Shack?
yeah.
Good,
That's good.
good. Yeah.
That's no problem.
All right, now, as I said, this is a very simple conclusion that we can get to now, which is that we can also express these annihilation operators, the curved space, or let me say it differently. What we want to do is look at this question. What are the curved space annihilation operators going to do when they hit, I'm sorry, what are the flat space annihilation operators going to do when they hit the curved space vacuum? And in general, they're not going to give us 0. And that will mean, so I'm going to say not equal to 0 in general, and that will mean then that the curved space time has induced the creation of flat space particles. In other words, if you look at the curved space vacuum with a detector that detects flat space particles, you're going to get non-zero result. Is that a question?
Yes. I think this connects back to something you said earlier that I had a little question about. You said we want to assume the same vacuum. So if we go from a flat space to a curved space, we're assuming the same vacuum.
No, I didn't mean to say that. If I said that, that was a miss.
Well, I may have misunderstood. Because my question is this. So you
what we are assuming is, we're assuming the same field.
Well, same field is what I meant. I said vacuum, did I? I meant field.
Yeah.
Okay, so in my mind, I'm trying to figure out exactly what that means. You have, say, a sheet of paper, it's flat, You have a field on it. Now you bend the sheet of paper, it's curved. Does that mean your field just, does it curve with it? Does it stay?
Or does it fill in the space everywhere over the whole curve?
I'm trying to figure out what this means when you say the same
You
field.
still have a notion of coordinates, right?
Yeah, you can still
matter what
describe
you
a.
so you-
All right,
So
well, I mean,
is that what
certainly
we're
if
doing?
this is flat space and this is curved space, the field lives in the space, in both spaces.
So here's your field, there's your space, it bends. Does the field stay here, or does the field curve with it?
Field curves with it.
But I guess the idea is that the field is you're just assigning a value to each point in space time, right?
Yeah.
And so that's the same, you just
yeah.
assign the same
This-
value.
this
I
goes
just wanted to
back
make sure I understood what he meant.
I'm tentatively going with Austin here on
This
this.
goes back to something you sent me a long time ago that I think it was that coordinates are not physical, but points in space-time are physical.
Yeah,
I guess if we,
yeah.
So the same value of the field follows the point.
Right. In any event, this is what people who discuss this do. And so what we want to look at then is this equation. And the way we can do that is get a formula for A0n. Well, we have our formula for A0n. And we recall that A0n is essentially F0n on phi. So this is F0n on phi on the curved space vacuum, right? A0n is this thing. We switch to this discrete notation, which I should have done in the beginning because it's so much simpler conceptually. But now, we've expressed the F0n this way, and the F0n's then are a sum on m of alpha nm. These things, by the way, the alphas and the betas are called Bogoliubov coefficients. And I'm going to write to one of my, or two of my Russian friends and ask them how to pronounce and spell Bogoliubov. In any event, we'll have here F0m plus beta nm F0m star in a product with phi on the vacuum. And now these guys, F0m with phi, they are giving us the ordinary annihilation operators, and they annihilate the vacuum. But what we're left with is this sum of beta nm, the inner product of F0m star with phi 0. And of course this we already know, this is the creation operators. So this is the sum on m beta nm, the flat space creation operators on the vacuum.
So I have one more question. The F0n is the bottom equation here, right? And it looks like you substituted the equation above for it.
Yes.
Yeah, I think you're right. That's not going to make any difference, but you're
No,
right.
I think it's.
This should be a star,
And that should
and
be
this
a
should be a
minus.
minus sign.
And the beta, should that also be a star?
And then you should take this.
No, I think, well, I did not, This is what Davies
Okay.
wrote. It could have a typo. I'm going to have to rederive it all. And if you use a discrete notation, all the derivations are much simpler. Yeah.
I was gonna say also you should get rid of the zeros that you have there, right? If you're expanding your flat space mode functions in terms of your curved space mode functions, right? See on the right side of the equation, your f's have zeros, and they should not have zeros.
Yeah, we don't need the zeros on the right anymore. Since they are.
Yeah, since it's in the.
Oh.
This is hard.
Yeah, I think you're right. I screwed up again. So this is F0n.
Yeah.
And now we're expressed. Ah, yes, you're right.
So.
You're right. Right. And so then F star, so there's no zero here. But on the other hand, the creation operators of curved space on the vacuum of curved space, this creates a particle, a curved space particle. And so this shows you then, this is the basic idea behind I think all of these effects. In other words, the Hawking radiation and is that you have outside a black hole, you have an intense gravitational field. That intense gravitational field means that the vacuum of that is a vacuum that has, it's a vacuum in which the flat space annihilation operators acting on it are partly like the curved space creation operators. And so you've got particle creation.
So this guy, Bogoliubov, he was a 2-time recipient of the Stalin Prize.
The Stalin Prize?
Stalin Prize, and also a 2-time recipient of the USSR State Prize.
Nice.
So he's like, this was really hard. That the Soviets thought that this was hard enough to win the highest civilian honor.
Yeah.
Stalin himself appreciated this.
For sure.
He also, I think, won the Dirac medal and the Max Planck medal. So that's pretty cool. This is really neat.
Yeah, this Bogoliubov transformation has implications all over physics. I guess like quantum optics.
All right, I guess we can stop.